Imagine a reality where everything you experience is just a two-dimensional projection of a hidden layer of the universe. The concept of a holographic universe suggests that all the stars, galaxies, and even you might be part of a cosmic hologram. This idea, which sounds like science fiction, has gained serious attention in the field of theoretical physics and cosmology. The holographic principle proposes that everything we perceive in 3 dimensions could be encoded on a 2-dimensional surface, much like how a hologram works. This radical theory challenges our understanding of the universe and suggests that space, time, and matter might not be what they appear to be at first glance. It all began with a surprising discovery related to black holes, which are among the most mysterious and extreme objects in the universe. In the 1970s, physicist Jacob Bekenstein made a groundbreaking realization about the entropy of black holes, which measures the amount of information contained within them. He found that the entropy of a black hole is proportional to its surface area, not its volume, which defied expectations based on traditional physics. This discovery laid the groundwork for the idea that all the information about a black hole might be stored on its surface, rather than inside it. Soon after, Stephen Hawking added to this by showing that black holes emit radiation, now called Hawking radiation, further deepening the mystery. The realization that information might be stored on the surface of a black hole inspired physicists like Gerard 't Hooft and Leonard Susskind to develop the holographic principle. They proposed that the entire universe could work the same way, with all the information about our 3D world being stored on a distant 2-dimensional boundary. This 2-dimensional boundary could be thought of as the skin of the universe, encoding everything we experience within the cosmos. In this view, the 3-dimensional objects we see and interact with are projections of information that exists on this cosmic boundary. But how could something as vast and complex as the universe be reduced to information on a 2D surface? To understand, it helps to think about information in physics, which describes the state of every particle in the universe. In classical physics, information includes the position, momentum, and energy of every particle. In quantum mechanics, the information is encoded in the quantum states of particles, which can exist in superpositions of multiple possibilities. The holographic principle suggests that all of this information, every atom, every galaxy, and even the fabric of space-time itself, might be encoded on a 2D surface. In this way, the 3D world we experience is much like a hologram, where a 2D image creates the illusion of depth and structure. One of the most exciting aspects of the holographic principle is its potential to solve some of the biggest mysteries in physics. For example, the principle could help resolve the so-called information paradox of black holes, which has puzzled physicists for decades. The information paradox arises because, according to classical physics, information about objects falling into a black hole appears to be lost forever. However, the laws of quantum mechanics suggest that information cannot be destroyed, leading to a fundamental conflict between the two theories. The holographic principle offers a way to resolve this paradox by proposing that the information about objects falling into a black hole is stored on the event horizon, the black hole's surface. This would mean that even though objects disappear into the black hole's interior, their information remains encoded on the 2D surface, preserving the laws of quantum mechanics. The holographic universe theory also ties into string theory, a branch of physics that seeks to unify general relativity and quantum mechanics. String theory posits that the fundamental building blocks of the universe are not particles, but tiny, vibrating strings that exist in multiple dimensions. In certain versions of string theory, there is a connection between the physics of higher dimensional spaces and the physics of their boundaries. This connection, known as the A-CFT correspondence, suggests that the physics of a higher dimensional space, like our universe, can be described by a lower dimensional theory on its boundary. The A-CFT correspondence has provided a powerful mathematical framework for understanding the holographic principle and how it might apply to our universe. One of the most famous examples of this is the work of physicist Juan Maldacena, who showed how a universe with gravity could emerge from a universe without gravity in a lower dimension. Maldacena's work has been a major breakthrough in string theory and has given the holographic principle a solid mathematical foundation. But what does all this mean for our understanding of reality? If the holographic principle is correct, it could fundamentally change how we think about space, time, and matter. It suggests that the three-dimensional world we experience is not the real reality, but rather a projection from a deeper, more fundamental layer of the universe. In this view, space and time themselves might be emergent properties, arising from the information encoded on a two-dimensional surface. This would mean that the distinction between here and there might be less meaningful than we think, as everything could be connected through the underlying structure of the universe. The holographic principle also challenges our ideas about what is real. Much like how a hologram is a real object, but its image is dependent on the projection of light, our universe could be real, but its structure might be more complex than we can observe. Some physicists have even suggested that the holographic principle could help bridge the gap between quantum mechanics and general relativity, two of the most successful but incompatible theories in physics. Quantum mechanics describes the behavior of the smallest particles in the universe, while general relativity describes how gravity works on large scales. Unifying these two theories is one of the ultimate goals of physics, and the holographic universe might offer a pathway toward that goal. While the holographic universe theory remains largely theoretical, there have been some attempts to test it experimentally. In 2017, researchers at Fermilab conducted an experiment called the Holometer, which was designed to detect tiny quantum-scale vibrations in space-time. These vibrations, if detected, could provide evidence that space-time has a holographic structure, much like the surface of a hologram. Although the results of the Holometer experiment were inconclusive, it was an important step toward testing the holographic principle and exploring the nature of reality. The idea of a holographic universe also has philosophical implications, as it forces us to reconsider our place in the cosmos. If our reality is just a projection, then the real reality might lie beyond our ability to observe or comprehend. This raises profound questions about the nature of consciousness, free will, and the relationship between mind and matter. Are we simply observers in a holographic universe, or are we part of the underlying information that creates the projection? These are questions that may take decades or even centuries to answer, but they are at the cutting edge of science and philosophy today. As we continue to explore the mysteries of the universe, we may one day discover whether our reality is truly a cosmic hologram. Whether or not the holographic principle is correct, it offers a tantalizing glimpse into the deep, underlying structure of the cosmos. In the end, the holographic universe theory challenges us to expand our minds and question our understanding of reality. It pushes the boundaries of what we know about space, time, and existence itself. Thanks for joining us on this journey through the holographic universe, a concept that has the potential to revolutionize our understanding of the cosmos. Be sure to subscribe for more explorations into the mysteries of science, philosophy, and the universe. Until next time, keep questioning, stay curious, and never stop exploring the wonders of reality.